Well, thank you all for being here today. I'm going to start by saying I'm going to follow up on a lot of the concepts that were already talked about and reinforce those a bit. So the moderators did a great job of organizing this session because we're doing a really good job here. So I'm going to talk to you all today about Portland limestone cement variability and use in high early strength concrete mixtures. My name is Michelle Cooper. I'm from the Federal Highway Administration, but first a little bit about who I am. I have a Bachelor of Science in Civil Engineering from Virginia Tech. Then I worked at the National Institute of Standards and Technology in their concrete laboratory, and then got a Master of Science in Civil Engineering from University of Illinois, Urbana-Champaign. Then I worked as a forensic structural engineer before moving on to become a concrete materials research engineer at Turner Fairbank Highway Research Center. And I'm currently the concrete laboratory manager there. And I'm also working on a PhD in concrete sustainability at Michigan Tech. So a lot of people worked on the results that I'm going to be presenting here today. And those people include Luca Montanari, Dr. Maria Younger, myself, Dr. Payam Hosseini, Robert Marinello, and Dr. Scott Muzensky. So a few acronyms that I just want to describe. ACC is accelerator, AE is Aaron trained, HES is high early strength, and NAE is non-Aaron trained. These will all make more sense later on. So first off, why is Federal Highway Administration performing research on PLC? And the answer is, we've heard you guys. We know that there's a lot of struggles happening in the industry, and we want to help. So we released a tech note back in the fall that describes implementation challenges and best practices to help mitigate some of those challenges we've been hearing about. And some of those best practices include using tools such as isothermal calorimetry, which was already talked about a lot, which is great. I'm going to talk about it some more, so we're all in agreement there. And this can help you investigate your early age reaction behavior in your PLCs, and additionally with your PLCs in combination with SCMs and admixtures. There's also differing sulfate content requirements for PLC concretes, and we'll talk about that more. And then evaluating your production variation, first in your OPCs before you make that transition. For some of you, it's already a little too late. But understanding your production variability before making this transition will really help you understand what to expect when you make that switch. So I'm going to be talking in two different topics today. So I've sort of split my presentation in two. So the first topic will be on PLC variability, and the second on use in high early strength mixtures. And in order to do that, first I want to just describe hydration kinetics a little bit more. So we got some great comments on it already, but for those of you who weren't quite there, first there is an acceleration phase. So you see that there, and then you have these two peaks in an ideal world, and then you have that deceleration period. And these hydration kinetics can relate to your performance and your reactivity through the rate of reaction and the magnitude of reaction. So talking about PLC variability, what are limestone's effects in our cementitious matrix? You have a nucleation effect, so it acts as a seeding to allow more reaction products to start growing and developing. It has a particle packing effect. So if you think about coarse aggregates in a tube, and there's all these air voids in between those coarse aggregates, if you pour sand into it, then you have less air voids between your coarse aggregates, right? It takes up all that space. So limestone acts the same way in a cementitious matrix. And then there's also the chemical effect that Dr. Birken-Ishgor was talking about, which your limestone reacts with your alumina source to develop ettringite and hemi-monocarboaluminates. So in our PLC variability study, we looked at 16 different PLCs from around the country. And you can see a map here of where those PLCs somewhat came from. So looking at our Blaine fineness, we saw a range in those PLCs from 400 to about 430. And compared to our reference cement at 380, that's a little bit higher. So that's what we'd expect to see, but there is a range there. Looking at density, we received density range from around 3.0 to 3.12, and our reference OPC cement is around 3.12. So again, we generally have a lower density in our PLCs compared to our OPCs. Looking at calcium carbonate contents, we measured anywhere from 5 to 17%, which is a big variation, and that goes back to what Stephanie was talking about as well, with those calcium carbonate contents being all the way across the board. So again, this makes sense compared to our OPC samples because of C150 and C595 requirements, but that is a pretty big range. And then looking at sulfation, so this is coming back to our hydration kinetics. We were able to distribute our 16 different PLCs into 5 different sulfation level categories. And those categories included properly sulfated, 3 close peaks, overlapping A-light and illuminate peaks, higher illuminate peak than the A-light peak, and 4 peaks. But what you really need to know from this is just with 5 different categories of behavior, that's a lot of differences in the possibilities for performance. So understanding what your behavior might be will also help you understand that performance you should expect. So how do those things correlate? So our 3-day and 7-day total heat release correlated really well, which of course makes a lot of sense. Most of your reaction is happening in the first 3 days, and it's only going to go up from there. So your 7 and 3 days should be that similar. Then your 7-day total heat release is very related to your water-cement ratio. Once again, this makes a lot of sense. Once your reactions are happening, anything that's happening in those later ages is highly related to how much water is left in the system to cause reaction. And then our density and our calcium carbonate content had a pretty high negative correlation. And once again, that makes sense. Our calcium carbonate, that's somewhat limestone, and that has a lower density. So we would expect to see this lower density. So how can PLC characteristics affect our performance? Fineness, density, and calcium carbonate content are all related to each other, and they can all affect each other in different ways. Sulfate levels can affect your setting time and your strength development. And your fineness can affect your air content, your slump, your water demand, and your shrinkage, and those all affect your durability. And then looking at these in combination with SCMs, as I said, I'm reinforcing a lot of the points already brought up. But there's a lot of differences in these hydration kinetics that we see from one cement to another, from one category of sulfation level to another, and depending on your SCM content and the SCM itself. Is your SCM highly reactive or less reactive? So I have a summary here, but really what I want you guys to take away from this is that there's a lot of differences in the PLCs that we're making. And those differences change our performance in different ways. And we can use all of those differences to better understand what we want from the product, to better utilize them to get what performance we're actually looking for, and to better our mix designs. So I already mentioned that we have a tech note that's already available, and we're working on a couple more things. So we'll have a PLC variability tech note coming out, hopefully in just a few months, and then a journal paper on determining the sulfation level of PLC using isothermal calorimetry. So now switching gears into high early strength mixtures. So our objective here was to highlight the potential differences when switching from OPC to PLC and high early strength concretes. So we used set accelerators and corrosion inhibitors and polycarboxylate high range water reducer to ensure workability. And we used both high reactivity SCM and low reactivity SCM. We had a few different mix designs. I'm going to focus mostly on the OPC and the PLC. But what you need to see here is that a set of those had accelerating admixture, and then another set did not. So looking at our normalized heat flows, and this is, once again, back to those hydration kinetics, gotta love the basics. Whoa, went too far. There we go. I apologize, on my screen, it has the dots, so you can actually differentiate all of the different lines, but on this screen here, you can't see them, so my apologies. The top one is actually OPC on the left, and then right below that is PLC, so OPC on the top, PLC right below that. And you can see there's just a little bit higher of a peak with the OPC, but we're receiving the same general trends for all of those figures on the left. And then with accelerators, the reactions are happening so quickly that we can't even see the acceleration periods. But we are seeing that our PLC, which is the highest curve there, actually has a higher magnitude of normalized heat flow compared to our OPC. So looking at cumulative heat released, we can see that our PLC, our OPC, and our PLC with our highly reactive SCM have very similar results with and without accelerators, and even more so with accelerators. So with that, we can see that we're getting a similar performance. Looking at some mortar cube strengths, you can see very similar mortar cube strengths at 1 and 7 days for our OPC and our PLC. It's a little bit lower for our PLC at 28 days, but by that time, you've probably got what you needed from your high early strength mix, right? You wanted that really rapid time frame. And then looking at porosity, without accelerators, our PLC and our OPC do a really good job. They're right next to each other, sitting there hanging out. And then with accelerators, at 1 day, you can see that our porosity is very similar. Sorry, there's some delays on the screens. So we have a publication coming out that will also talk about this. But in summary, can we use PLC in high early strength concrete mixtures? Yes, yes we can. Our PLC can replace OPC in high early strength mixtures with and without SCMs and accelerating admixtures while meeting state high early strength requirements. And this depends on SCM replacement levels, SCM reactivity and type, exposure class, reopening strength and time requirements, and the inclusion of accelerators can improve early degree of reaction and compressive strength for all of these systems.